Okay, let's start this session. Thank you very much for being in this IEEE CEDA luncheon keynote. It's our very big pleasure to have such a distinguished speaker with us today, which I will introduce in a few minutes. But I want to thank you all for such a quick lunch and coming over here instead of staying for a more leisurely meal and talking with all your friends. It's fantastic that we're all here together 3 years after the fact, and let's leave it at that. So my name is Miguel Silveira. I'm the president-elect of CEDA. I'm here in lieu of Gijun Nan, who's the current president. He unfortunately had a small issue with his passport and could not come. But before introducing the keynote, I want to just give you a few brief words about CEDA and what we do at the Council. And while that happens, more people will come in and find their spots and all that, so we'll go slowly. So CEDA is one of the divisions in IEEE. It's a council, which is sort of like a society, but not quite, but for most purposes, it's about the same. It was formed quite some time ago with the help of several people who are in this room, and it wants to be sort of the center of activities that relate to electronic design automation within IEEE. So it was realized quite some time ago that there were activities in EDA in many different areas, which still exist, but they were scattered, and there was an effort to try and sort of bring them all together under the same umbrella, and that's how CEDA was formed. It's now, it has several member societies, so there are people in antennas and propagation, circuits and systems, computer, electron devices, microwave theory and techniques, solid states, et cetera, et cetera. All of them are society members from their respective societies, but they all contribute to CEDA as a whole, because they all sort of have this commonality that we all have, that we work in different aspects of design automation. The vision or the goal of CEDA, of course, is to be, as it says here, the leading provider in IEEE, sort of the gateway from IEEE for technical information for the community in EDA. So what do? We have a lot of publications, a few publications that are shown here. I'm sure everyone knows TCAD, Embedded Systems Ladder, Design and Test, which we revamped a few years ago, and it's now doing extremely well as a magazine, and also the Journal on Exploratory Solid State Computational Devices and Circuits, and also the Transactions on Signal and Power Integrity, which is not shown here. It's a new journal that we're also involved here. Our publications, I'm sure you all publish there, and I want to encourage you to continue to do so, are the premier publications in our field. CEDA also delivers several awards for people. You saw today that Nani was the recipient of the Phil Kaufman Award, which is co-sponsored by CEDA. We also deliver the Richard Newton Technical Impact Award, which we handed out at DAC in July later. The Donald Peterson Best Paper Award from TCAD. The Ernie Koo Early Career Award for young people starting their careers and getting deserved recognition. The William McCullough Best Paper Award for ICCAD, and then a few other distinguished and outstanding service. And of course, we also, within IEEE, fulfill our function by nominating our most distinguished researchers, the people that do the highest contributions for IEEE fellowship. We are starting a new CEDA award for supporting participation of women in engineering and International Leadership Conference. So we have this distinguished lecture program. We started it quite some years ago. Of course, it was interrupted by COVID in the normal form that we would meet, but it continued. So we have lunch and keynotes at major conferences, ASP DAC, DATE here, DAC, ICCAD, and also at ES Week. And we also have a program for distinguished lectures which may do visits or provide lectures online to anywhere in the world. So we support EDA-related conferences and EDA-related contests. There's lots of contests going on at all major conferences and also outside of the conferences for students, which we think obviously is extremely important because, as we all know, probably the biggest challenge we have facing us, although Jan in his talk might present a few others, is to make sure that we bring new people into our field. That's a major, major problem. We have chapters worldwide. That's one way of engaging with our members and also one way of bringing students into our activities and getting them excited in the fields that touch on EDA. If you don't have a chapter nearby where you live, we strongly encourage you to get in touch with us and start your chapter or collaborate with some colleagues to start your chapter in your location. So these are some other ways of getting in touch with us. And I guess we now have a fairly packed room, so I won't delay it too much with chit talk, and I'll introduce our speaker. It is with great pleasure that we're welcoming Professor Jan Rabaey. Professor Rabaey is a professor emeritus at the graduate school at the EECS department at UC Berkeley. He was the Donald Peterson Distinguished Professor at EECS, and he was also, for many years, the EE division leader in the department. He brings with us strong experience, not just from his academic experience, but also from industrial experience. He was actually at IMEC before going to Berkeley, and he is now again connected with IMEC because he is he's in the System Technology Co-Optimization Division of IMEC. He's the CTO of that division. He founded many labs at Berkeley, the Berkeley Wireless, which many of us, I'm sure, have heard, the Swarm Lab also, and his work is very well known for the many contributions that he introduced in low-power IC, advanced wireless, mobile devices, et cetera, et cetera. He is the recipient of too many awards for me to nominate here, including awards from CEDA, CAS, SRC, the Semiconductor Industry Alliance, and so on and so on. We'd spend the entire hour here talking about these awards, so I don't want to do that. I'm sure everyone is tired of listening to me, so without further ado, Jan, please.
Well, it's working. Thank you. Thank you, Luis, for your kind introduction. It's a pleasure for me to be here, definitely at CEDA. I remember the early days of CEDA. I was actually involved in that, and I'm so pleased to see this as a thriving community. So today I'm going to talk a little bit about bringing the magic back to design. And I think you will understand while I'm walking through the talk what I basically intend with that. So since I'm retired emeritus and things like that, I actually can talk a little bit about the past. But also, I hope I can talk a little bit about the future. So my talk today will be about the past, the now, and the future. And we'll start with the now. It is amazing, right? If you look at it, if you've been in this community of IT design, how much impact all those things have had on society, are having on society. Technology is everywhere. It basically is in every aspect of society, and semiconductors are throttling this whole thing. So everything runs on microprocessors. Almost any innovative tactic we can take up for business and things like that will depend on semiconductors. So an amazing success story, but also somewhat of a scary one. The challenge right now is that we have so much success that we really are running into a shortage of qualified people. And that's true in every part of the world. You go to Asia, you go to Europe, you go to the US, we are basically looking for skilled people in the domain of chip manufacturing, but also all the way up to the design chain. So that's a challenge that we definitely in the academic world, but in the overall educational world should really be worried about and try to figure out how to address it. And again, some of those things are quite obvious of why we have that particular problem. This is, by the way, I think an exaggerated curve. It's also an older one, which shows actually that over the years, people that got involved in design and electronics and things like that moved over to the software space. And that's true everywhere. You look at computer science department, data science departments and things like that, all over the world are thriving. And we have a really hard time filling up our electrical engineering departments, definitely in the design space. So we need to do something about this. And we have to figure out why that is. But again, what I'm going to try to do in this talk is maybe giving some perception of what we can do about it. What we can do to make our field really exciting again. And that's really the topic of this talk, how to make electronic design exciting again. And that's the right point for me to go back to the future. Once it was very exciting, it really attracted large groups of people. What are the vectors that were aligned at a point in time to really attract so many people to the space? So, inspiration from the past. I was a very young graduate student around the late 70s when a very influential work came out. I'm going to talk about actually about the 70s and the 80s. A very influential work came out. It's, a lot of you have seen it. It's the book by Mead and Conway, and it's called Introduction to VLSI Design. And it did some remarkable things. If you read through this book, and even today, it basically created somewhat of a revolution, a new way of thinking about how electronic systems are designed. And the most important one was that it created an interface. Something before electronic design was a craft, where you have to basically understand all the bits and pieces to create something. It was basically custom all the way from the transistor or the technology to basically the artifact you try to design. What Mead and Conway did was say, well, we need to have a horizontal separation between the manufacturing side and the basically design side. It was called design rules, and it came actually with a language where you could describe a design in a very tangible way. So as a result of that, us as circuit designers didn't have to worry that much anymore how the transistor was being designed, what was happening with this in the manufacturing plant, and so on and so forth. So the intermediate language was called the CIF, or the Caltech Intermediate Form. And I remember very well, it was a very useful tool because now I can start writing tools that generate CIF, and from there on, we just ship it to the factory. The horizontalization of manufacturing started. The other thing it did, basically, what happened at the same time, is that some funding sources, like DARPA, understood that and actually created the capability for universities to start doing all kinds of digital and analog design and make them fabricated for a very reasonable cost. So they funded MOSIS, and MOSIS basically enabled the concept of multi-project wafer services, where universities easily could come together, put designs together, get them manufactured, and in a fairly short time get them back and measure them. It was really exciting. You could make things and see them come back and test them. Now, this inspired a broad range of folks which are not purely circuit designers, but basically software people, to start designing tools. There was the magic VLSI layout tool that was written by John Oosterhout. And by the way, John Oosterhout was a computer scientist, not a hardware person. There was obviously SPICE, that was arisen from Berkeley earlier before that, and many versions of it, and switch level simulators, and so on and so on and so forth, as well as databases and other things. So the set of tools that were generated by universities, and they were open source, they were public domain and accessible to everyone. So you just download them and you could play with the tool, you get to the source code, and so on and so forth. So it gave us access to a tool base that was open. The other thing that basically arose at that point in time is that if you want to now automate the process even further, we need to do so. You cannot just do anything. because it's really hard to write development, basically layout tools and things like that, if you allow everything to happen. So design methodology got born by the concept of what I call freedom from choice. Right? Basically, restricting what you could do can help you to make better tools. And a whole bunch of those tools basically rose. The first one said, okay, maybe if we just allow two-level logic, we can actually write a tool that generates the logic, optimizes, and so on and so forth, and you can map it into structured layouts such as PLAs. And we can optimize those things up to hell. So there's a bunch of tools that came out. Again, the group of people like Bob Brayton and so on and so forth created tools, and again, they shared them around. Freedom from choice. It was a very restricting, but we can choose, make it work, and so on. And you can bring this to the next level. Well, so okay, maybe PLAs were too restrictive as a structure. We really would like to do multi-level logic. And yes, we can do multi-level logic optimization, and we can actually turn this into layouts by using something which is called standard cells. And I think Herman Beek is somewhere in the audience here today. Basically worked some of the early tools to do place and route for standard cells, which is now the common tool for every single logic that's being designed. But again, it's about freedom of choice. Right? You basically are fixed in the cells, where you place them, and so on and so forth. So all those kind of things coming together created that vibrancy, created that opportunity to do many things. But ultimately, we started realizing, and some of this is, well, maybe design should become a software process. The whole concept of silicon compilers. Can we write a high-level language and translate that high-level language into physical artifacts? And I just show some examples here that basically show that if you really have a constricted flow, you actually can go and work your way from high level, step by step, into intermediate, generate architectures, synthesize those architectures, make them manufactured. Also, high-level languages emerged. They were not very good. Basically, VHDL came from the defense community, Verilog more from the EDA community. Both of them were hardware languages written by hardware designers. So as a result of that, they were not very good. But at least they made us something happen. So it didn't matter that they were good or bad. The fact that we had languages helped us to basically move forward and create things. So again, that's the next step, raising of abstraction levels. So this is what has happened. So we basically, as a result, by having the set of things, circuit simulation, logic level, synthesis, place, and route, we can do more and more complex things. The productivity of designers improved dramatically. Okay? And this also gave rise to a vibrant industry. The EDA industry became very big. This is a slide I stole from Richard Newton. He gave it in 1992. And then he repeated it in a keynote talk at DAC in 1995. And he compared the life and birth of EDA companies with the Hertzsprung-Russell model, which is how stars evolve over time. Basically, the life cycle of a star, where you have, stars start with basically with very high energy, very high luminosity, and then gradually kind of slow down, and they turn either into supergiants or they basically go supernova. So he compared that, and he interposed the various CAD companies on it. But what it showed is you had a really vibrant kind of creation of new companies, small companies that really created a lot of luminosity but didn't have a lot of mass. And then gradually they got bigger and bigger, still losing luminosity, and ultimately turned into red giants. And red giants, after a while, basically disappeared. That was the story. And you look at some names here, this is from 1992. As you realize, most of those names are gone. But not all of them. The idea that actually some of those companies would become too big and kind of devolve themselves and explode didn't happen. Actually, in reality, we still have the same 3 big players out there, but we don't have a lot of star birth anymore. There's not more stars flying up and coming up every day. EDA startups have been very hard to make over the last century or so, or a couple of decades or so. All right. So after that, I think we went into the interregnum. Again, it's a domain that really design got very popular, and then suddenly it kind of flattened out, leveled out. Just to show you how this happened, or why this, or some of the reasons why this happened, if you look at the design automation and the design world, and you look at the conferences, DAC used to be about 15 to 20,000 people attending it around the year 2000. Since about 2005, 7, it has gotten flat on a way lower level. It might be improving again, it might go back again, but we see definitely a problem here. Academic research has been plateauing. It's been very hard to hire new faculty in the world of EDA. Design might be a little bit easier, but EDA has been a domain that has not seen a lot of growth in terms of academic recruiting. EDA research groups, as a result of that, have basically disappeared. In Berkeley, we had a whole crowd of people. Now it's very tiny. We see little new star formation, and overall, the advances have been slowing down. So, kind of sad. And one of the reasons of this, I think there's a couple of reasons why this happened, right? Obviously, the whole thing but I believe that at some point in time, the whole discussion about design has turned into how to manage complexity. Complexity, because we knew that Moore's law was strong. We would get a new technology generation every 2 years. We could do more complex things. And then the question is, how do you deal with the complexity? How many cores can I put down on a chip? How many transistors can I reasonably put on a die? Now, that's a great topic, and it's a very important one. It really drove the industry forward by doing so, but there was little room for academia in there. Academia is not very good at doing very complex things. They're good in ideas, but they're not good in complex things. Also, rather than looking upwards towards the system level, most of the design automation world has been looking downward. Oh, we have a new transistor with more new features. How can I make sure that those transistors work well? How do we do timing analysis, and so on and so forth on those very complex things? Again, a good topic, but not something that basically is revolutionary. So, question is, what can we do about that? So, here is where we are. One thing has been added, however. I think one little block which has been very important is the block of reuse. Deal with complexity, we take blocks that we can repeat over and over again, and that's why we can make complex chips. Many cores, many transistors on the die. So that's there. So the question is, what's next? Where are we going, and why is this really exciting again? So I think we're going to go to the roaring 20s again. And that's where we are right now. So let's have a great party and make EDA and design attractive again. And the big driver behind this is right on this curve here. You've seen it many, many times before. But actually this driver, that engine of the industry, which is Moore's law, or whatever law you're talking about, where we're seeing a slowdown in density increase, we see a slowdown in performance, we don't see the energy savings anymore that we used to have. So it's a time for change. We really need to rethink if we want to make our industry move forward in the same rate. It's a time for new magic. And I think there's an important statement here, and I think I want to put it to all of you, is, and I'm going to repeat it again, be bold. This is a time of change, and I think in both industry and academia, we should take risks. In order to go to something new, you have to take a risk. And we're not taking enough risks in our community. So, here's kind of the world of today. And here's the microelectronic cosmos. It's a very broad space, because electronics is everywhere. So on one side, you have this huge data centers with racks of computers, the complexity thing. On the other side, we are basically building electronics that is basically integrating into the world. It's basically becoming part of our physical world. You call it IoT, you call it sensor network, you name it, but it's something that basically figures out. And then you have the thing in between, which is called the edge. So this is what our systems are starting to look at. Very distributed, but very different as well. Solutions that work for the cyber world are not going to be the solutions that work for the natural world. There's definitely a differentiation between those. Same time, while we basically are forming this complete new vision of how our IT platform should look like, there's another thing that's happening. I think we're back at a technology explosion time. At every level of the stack, we're seeing new devices. They might not be necessarily switches, but new devices that can do amazing functionality. Think about quantum devices. Think about optical devices. Think about those. Think about ferroelectrics. All those kind of things are creating new things. We also see extreme heterogeneity. We're not just talking about computing anymore. It is about computing, storage, sensing, actuation, communication, energy. So the scope of things we're looking at is getting much wider. The computational models are changing. In a very short time, AI has gone from something of a side thing to driving everything. So we should be aware of that and we should use it. But you have other ones. It's not just AI. It's also quantum. It's neural. All those type of things, models of computation that are novel or different, and that we should basically harness as well. Advanced packaging, 3D integration, no question. We're going to the third dimension. We finished up with the second one. So third dimension integration is the other thing. So there's many, many, many opportunities to be innovative. So let's go step by step. Nothing happens overnight. So we can move forward one by one. First one is, again, go back to Verilog and VHDL. Those things were made in the 1980s. Long time ago. If I look at the computer science world, it has changed dramatically. How people program, how they basically capture information and things like that has changed substantially. And it's going to change again. Again, if you think about what ChatGPT can do for programming, you will see new ways of capturing intent. So Java, Python, TensorFlow, PyTorch, and things like that, all those things are basically making its inroads into the design flow. And that's the way we should capture design. We have also, again, back to the early days, open source. Open source, public domain, accessible type hardware. Really important because, as I said before, complexity was killing academic research. If we can encapsulate that complexity, if we can make available large building blocks to the academic community, but also the startup community and the industry community, we'll basically give another boost. And RISC-V for it is a perfect example. RISC-V, I believe, is overhauling a lot of the established type of practices. But it's not just that. It's great if I can put a little processor on a chip, or 20 or 30, but you need everything of the whole system. So you need RISC-V generators, and I need vector processors, and I need custom accelerators, memory subsystems, cache systems, bus network. Having those available in a public domain platform is really crucial. That enables people all over the place to basically start thinking about, hey, we can do complex design again. It has to, however, come with the tools that support them. Software flows, to basically compile onto things, operating systems, high-level synthesis, as well as analog. Don't forget about analog, we need analog generators as well. And we need the simulation tools and the prototyping tools available to us to make that happen. So this is kind of a vision of if you create a platform like that, you make it available to everyone, you will see, again, a spurge of activity all over the academic space. And I just give one example here. This is an effort that some of my colleagues in Berkeley have been working on over the last number of years, Bora Nikolic and Sophia Shaw, and primarily it's a tool set called Chipyard. And Chipyard basically brings all those things together. It allows design reuse, it allows software reuse, public domain, open source, integrated design flows. So there's some link here if you're interested in that. But it shows again that we basically, as an academic community, now we can start dealing with that complexity and go to the next thing. Now, how important is it? Well, here's what you can do with this. So now for a couple of years, we've been running a class in Berkeley, which is, by the way, an undergraduate class, final year, senior year, fourth year. where students basically start from scratch and design a system on a chip in 4 months, and they tape it out. And this is not in any technology. This, by the way, is in an Intel 16-nanometer technology. On the left side, you see a complete machine learning chip with a bunch of embedded cores. There's a micro mode that even has a wireless component, A to D converters, and all those kind of things on it. As I said, this is done in 4 months by a group of students and has been very successful. It started with 10 students, 20 students. Nowadays, we're up to about 60 to 70 students in the class. Now, it's an expensive undertaking. You need access to technology and things like that. But what we find is that companies are actually quite happy to support it because this is helping them to train new engineers that are trained in the next generation design, not in small gates or anything like that. The other one that's interesting is that, as I said, it's expensive, but it turns out that the various manufacturing players are starting to get interested in this. So you might have heard this, it was announced at ISSC that TSMC is now opening a vanilla 16-nanometer FinFET process. They give you the whole PDKs and everything in the model. They're not for real. You're not going to fabricate those things. But it opens them up to the academic community to start playing around in those advanced technologies. And if you're really good, you can even convince them that they give you the real PDKs and you can actually do real chips in those technologies, which are going all the way down to 7 nanometers. And then there's a lot of talk also about open domain PDKs and things like that. That's basically Google playing around in this space together with other companies. But the bottom line is people see there's a need for designers. Suddenly we see a change in attitude. So to me, this is a very positive change that allows us again to make design attractive in the academic community. The other initiative that is basically started as well is, which is called there's actually a couple of competing initiatives. It's called the American Semiconductor Academy, where we start thinking about sharing curricula, sharing courses, sharing shareware between various schools all over the country, but all over the world. And I think that's another very important initiative to think about. How can we boost the knowledge, the classes, all those type of things to make sure that we can educate lots of people. All right, so this is still 2D though. And as I said, the real world is going to go 3D. We have to really start thinking about heterogeneity, extreme heterogeneity, and more than 2D. And the concepts of chiplets, it was already mentioned before, interposers, memory subsystems, and so on and so forth, basically is where we're going to go. Now we have to make that accessible. We have to make that available not only to the few, but how can you make this cheap enough and accessible enough that we in universities can actually start doing designs and kind of realize what the potentials are of those designs to create new architectures, to create new ways of building particular functionality. So no doubt in my mind this is where to go, but there's plenty of work to be done. Because again, it is all about design, basically freedom from basically, what was it again? Here it is, freedom from choice. There we go. So in order to make this work, we're going to have to make some sacrifices. You're not going to basically put TSVs everywhere around. You're going to have to be stuck there. But even with that, we can do very interesting things. We can build systems that are very hard to build before. But ultimately, this is where I want to see this lead. Really thinking in 3D. Right now, a lot of our architectural thoughts are still 2D oriented. We really need to start to think about what would happen if I have a full 3D spectrum forward. Basically, the risk factor. And here's an example. This is a small startup company called Rain Electronics that is doing some of those risky things. They're building neurons where the axons are being vertical, being connected in various different ways. A very interesting usage of 3D technology that basically uses some of the advantages of 3D, not a 3D version of a 2D solution. Now, in order to make that happen, we need the capability to build it, right? As I said, it has to be cheap enough, accessible enough. And this is why I believe this time is very ripe. Governments all over the world are starting to realize that manufacturing of advanced circuits is very important. So in the US, there's an initiative beyond the NSTC and the CHIPS Act, which is called the Semiconductor Commons. And the Commons concept is really to have a set of labs spread around the country that allow us to build basically devices like this. On a small scale, build prototypes of 3D or 2.5D systems and be able to explore and expand on this. So the microelectronics commons, I think, is something that's under the making right now. The first set of bids have gone out. But to me, having that capability for university at minimal place to experiment with 2D and 3D integration is very important. And as I said, this is all funded by the fact that people realize that semiconductors is essential. So there's a whole bunch of, the money is there. Just like DARPA in the early days gave MOSIS, now you can start seeing all those CHIPS Act giving core functionality, hubs that basically do prototyping, and so on and so forth. We see cheap fabrication of novel things really happening again. All right, as I said, I will talk also about the future a bit. Now, the most important thing about the future that I think about is based on the following observation. But before I go there, I'm just going to give you a little wish list. Imagine that you could do this. Design tools and services that are distributed throughout the world, sitting on a server and personal computer just waiting to jump in action. Now, that seems to be something we already can do today. Tens of, perhaps hundreds of such tools and services linked together to evaluate trade-offs among a wide range of component architectural options. User interfaces that are automatically downloaded across the network when need is invoked. Agents that wander the network building repositories of interesting information. And services spanning chip design, packaging, rapid prototyping, assembly, test, and volume manufacturing. Sounds this is like perfect for our time right now, right? We see all this kind of distributed functionality emerge. So actually, this is not something I came up with. By the way, the last one is environments in which online training comes with the tool and the service, which will be nice as well. Now, this was, again, from not today, but it was actually in the keynote of Richard Newton at DAC in 1995. And he stated, such systems are not really that far off. We're not there yet, but it would be nice to have. So it was a great dream, and I think we still need to work on it. But let's go a little bit further. We need more. One thing we always observed is that computers build computers. If you think about it, every time we build a computer, we're going to use it as the way to build the next generation computing. And that's the way you bootstrap. Right? First, you start with an Applicon or a DAISY workstation. The DAISY workstation was used to build the Sun workstation. Sun workstation built the next generation. And now we built this massive set of computers everywhere around. So computers build computers. We have been building amazing computers recently. We should basically use them effectively to build our next generation. So first example, we have those massive cloud operations. So EDA should maximize the use of the cloud. There's no question about it. We have an unlimited amount of computation there on our hand. So EDA in the cloud should be driving semiconductor innovation. That's one. And an example of this is something you already heard about today, is this whole idea of digital twinning. Can you imagine that if I would now have a complete digital virtual flow sitting next to my physical flow, where novel devices can be injected in virtual form into actual systems to see what the impact would be. Or vice versa, that novel developed devices can be plugged into a virtual system to evaluate the impact. This would allow us to basically make a much faster analysis of if something is useful, is it worth spending more money on it, and so on and so forth. So this idea of basically virtual and physical prototypes that co-evolve would help us to speed up design from concept to validation a lot faster. Today, for instance, we have a lot of small ideas, but everybody always like, can you build a big prototype? But that's too expensive. Can I basically use virtual systems to actually show that my idea makes a lot of sense, saves power, and so on and so forth? So that's one thing that novel computers can do. The other one is that a lot of those big machines right now are all basically used to do AI, right? Google claims now, however, that using AI can help actually to design chips faster than humans. So what it leads to me as a conclusion is that what we should think about is AI building AI. So using AI to generate our next generation chips. And again, using AI chips to design better AI chips, and artificial intelligence may be better than human at designing microchips, I think is something we really should think about. It will be AI that will be building the next generation computers. I believe very strongly. So this is the extension that I see from the curves we had before, and we have to make happen. So remember reuse, chipyard was basically the kind of reuse to extreme, but nowadays we have a lot of AI-based design tools, but I really think that AI should be designing the next generation computers. Help us to do so. That, I think, is an important step forward. Now, this is all technology, and I'm going to finish this with kind of my belief is that in order to make big changes happen, you can do this in a number of ways. You can focus on the technology, you can focus on the pieces, but to me, it's always moonshots, dreams that can make big changes. And I think a lot of this next generation will be built for a particular purpose, moonshot ideas. And there's many of them. You can come up with them all together. Quantum computers, the compute continuum, that idea of a compute that goes spread from the world, from the IoT device, all the way to the edge and the core, and all in one system, is another interesting one. You heard a lot about the metaverse. I like the word mirror world a lot. Self-replicating computers, cognitive computers, and semi-organic computers. These are all interesting things to play around with. I'm just going to show you a couple of them. I think the compute continuum could, for instance, include data centers in space. Seems like a perfect place to put a lot of compute space. Cooling is very cheap. There's a lot of advantages to do so. But if you start doing that, you have to rethink the way you build a computer. It has to be self-correcting, right? Those things will fail. How do you build a machine that can live for 100 years and survive? If I want to send something on a mission to another star, it's going to have to run for 100 years. And how do you do that? Can I have healing, adaptation, self-replication, and so on and so forth? Just one example of what a moonshot could look like. Other moonshot is obviously this idea of cognitive computers, or where we intersperse the organic brain with the physical brain, making them work together in one particular continuum. Another example, can I build a brain-like functionality in the same volume and the same power of our human brain? So one or two cubic decimeters, 20 watts, same functionality. Is that something that's possible? Can we build something like that? And the last one, I think, is ultimately I believe that organics and physics will actually come together. The idea that actually can build analog, or basically organic neural brains, put them together on a silicon or whatever fabric, and make them work together as a computing entity. These are kind of some of those wild dreams that make us to do kind of the big steps. So, final reflections. I think we're at an inflection point. I also believe there's an absurd range of opportunities. There's many, many, many exciting things we can do. And obviously, they're going to be driven by societal concerns. Society is going to play a gigantic role in this, but also the acceleration of innovation in devices and technology. We need smart automation, well-defined interface. That's going to be so crucial, and a new vision on prototyping and manufacturing, which include, for instance, this digital twinning. But I also want to point out always, whenever you want to build something, it's going to always be important. It says, pick the right choices, freedom from choice. In the end, however, what I would like to see is somebody here in this room, or a couple of people in this room, generate the next version of Mead and Conway, the Mead and Conway of the 21st century. I think there's something we desperately need, and I'm looking forward to that. So thank you, and again, I'm just going back in the past. This is we in the early days of the 1980s. Thank you.
Thank you very much, Jan. I think we're all at the edge of our seats, so stealing a word from Jan's talk. So are there any questions from the audience that might have been inspired by some of the things that
Sure, such a talk can go without a question, right? So Andreas from Technical University of Munich. On the freedom from choice, could you give some more perspective on this, what it means for cognitive computing, for self-replicating computing? So this means all this DNA must already be set and you have no more choice in all these replications? Or second aspect of it is design. Do you see in the future the design still as it's still mostly done, namely that you have a design phase and a runtime? Or will chips, computers evolve during runtime to get from the 99.9% of the testing, the validation to 99.6 times 9?
So, good question. The first question was about freedom from choice. And with that, I mean is I don't intend to basically box everything up. No, you basically make some constraint in such a way that you can handle the problem. That's really the whole idea. And the same thing is true with cognitive computing. No, I don't want to be constrained everything, but you're going to basically set some rules. As a starter, say, that's what I'm going to live within. And maybe it's not the most optimal solution, but it allows me to come to a solution which is otherwise very hard. That's the whole idea. The second question was regarding the, let's see, runtime. Absolutely. I think the idea of a chip that from the time it's manufactured, that's it, I think is limiting. We really, again, we as humans evolve continuously. We learn or we forget, which is good too. It's good to forget occasionally. But now we adapt. And I think configurable, flexible platforms and things like that. In the bottom line, AI machines to a certain extent already are becoming that. Not in a way that it basically, because right now it's pure inference they're doing. But if you start putting learning and inference on the same device, it evolves. And you will see movement of functionality based on what works, what doesn't work very well, and things like that. So no, I believe in that continuous evolution of a particular design. No question.
Hi, thank you so much for the talk. My name is Dan. I'm a PhD student at University of Washington in Seattle. And so something you were talking about, and a lot of people talk about these days, is getting more young people into circuit design. But the calculus is simple. You'll make more money in software. The job is probably easier. And this is my experience when I did my undergrad in E. I think more of my friends got software jobs at Microsoft than went into hardware at any company. And so I'm curious, maybe based on what you saw at the class at Berkeley or just your experiences in general, how do we get more people into circuit design when there's so many other great options available for them?
That's an excellent question. Obviously, it's something that every single campus, I think, is, or department, electrical engineering department is discussing these days. But a couple of things, right? Obviously, the money factor plays a lot. And I think I've been putting the gauntlet a bunch of times to the semiconductor companies. If you're complaining all the time, basically raise your salaries. That's one. Now, the outrageous salary levels that the software companies were paying at the same time was also a problem, but that's being corrected right now. So there's some auto correction happening here. They were indeed going hayward, right? But still, though, you're totally right. Ultimately, the key thing about software is, I call it, it's a very short road to satisfaction. And you know, you go to your first software class, and at the end of the class, you do hello world, and you're already doing something. While typically in hardware, you have to go to a number of steps, right? You have to learn how to do. I think that can be overcome. These days, I have high school students that come up and say, hey, can I work on a project with you? And they're already doing basically Raspberry Pi programming, and they're already they already start playing with hardware. So early access and early success and feeling the thing that you build something is really important as well. And it can be done in a number of ways, but it's something we should pay close attention to. Again, that early road to satisfaction is very important. And again, but you're in the long term though, however, you're always right. Design is an inverted pyramid. There's going to be trillion people doing applications, and then there's some people sitting in between doing software, and the hardware base is always going to be smaller. So trying to be the same level, I think doesn't make sense. You have to realize it's always going to be a smaller community. But right now it's too small.
Renaud Gillon, CEDA Belgium. You mentioned quantum computing and the neural networks. Are we seeing kind of a revenge of analog based on the need to reduce power consumption?
Very good
And are there any challenges related to the architecture changes?
Sure. Now, short question, long answer. Obviously, right now, the digital we're doing today is constrained. If you think about from an energetic perspective, and ultimately, in the long term, anything is going to be driven by energetic. Right? Ultimately, if we want to do more dense computing, energetics will be the constraining factor. Digital is limited as it stands right now. We're not going to improve a lot on it. It's clear that analog has the capability to go a couple of steps beyond. Quantum does as well. Again, I always use the example of you look at your brain, that's why I threw out the gauntlet. Somebody can build me something with the computational capability of a brain within a cubic decimeter, and basically, if you can do that, you're going to basically leapfrog by a factor of 2 or 3 magnitudes. So, and the brain is obviously an analog, semi-discrete type of entity. Now, obviously, we don't understand, we cannot build large analog systems. It's very hard. We know how to do small ones, but ultimately, at some point in time, we get killed by noise, you get killed by basically variance, and so on and so forth. Now, the brain actually manages to deal with that. Right? There's actually regeneration going on in the brain. It eliminates noise through a set of mechanisms. So maybe this is what we could learn, and maybe we should study about how can we indeed build very large analog or discrete systems. That is an interesting target to go after. And again, we have to be broad, we have to basically take risks, and this is one of those risk ideas to think about. Yes?
So in the interest of keeping up with the program, I'm going to close this session, but Jan is going to stay here with myself, Robert, and I hope all of you, because I can see there are a lot of questions still to be asked and answered, and I'm sure Jan is more than happy to do so. But I want to thank Jan one more time for being our distinguished keynote speaker today.